Sinon, c'est tout.
Attends, je ne le vois pas. C'est bon comme ça? Yeah, that's the representation.
Oh, that is the presentation.
Yes.
Excellent.
Right.
Perfect. Well, thank you. So our next speaker is Nicolás.
The title is behind.
Exciting.
Is setting this on fire.
Setting this on fire. Great. Let's take it away.
All right. So good morning, everybody. I'm going to talk about flybys. So my inspiration here was AC/DC for the title of my talk, because basically what we're planning to do here is to set disks on fire through stellar flybys. So this is part of the lyrics. Shot down with flames, ain't it a shame to be shot down with flames, no shoot.
Can you sing it?
No, I'm not a good singer.
Tu peux arrêter de refaire le partage Zoom, c'est pas un...
Oh, okay.
Désolé.
No worries. Sorry.
Sur l'écran, ton écran, c'est ça.
I should stop this. So let's go back. Share. Is it working now?
Oui, c'est bon. Merci.
Okay. So the super cool effect. This is for Jan. We had a bet. There are many stupid effects in my presentation. So anyway, I'm gonna repeat it. So this is the takeaway of the talk. If you don't want to hear what I'm about to say, but there is a broad range of dramatic accretion events that may be linked to stellar multiplicity and stellar flybys with disks. Also, flybys are not necessarily harmful for planet formation, and I'm going to try to prove that context matters here. Then the third point is that flyby models may help to better interpret the emerging population of outbursting stars, but this link remains to be established. There was a very nice conference last year in Chile where we discussed this quite extensively, and there is kind of an emerging need to better understand outbursting stars in general. So why should disks and planets care about stellar flybys? The main reason is that we typically have this view of how things proceed from the gas cloud to the disk and then the planets. But actually, we know that this is just done for simplicity, and then in reality, this is far from being true. And we know that this typical scenario needs to be revised. And actually, this guy, John Herschel, was the first to start mapping the galaxy in the search of binary stars. And if, in his view, basically, this is what should happen. You should have several stars whenever you have these clouds, and that will lead to the formation of multiple stellar systems with disks. And in these regions, you might have encounters between stars, which will basically drive accretion. You might have precession of the disk. You can also set the disk size and also the masses. So we need to take this into account. And this is why my point here over the last years has been to prove that stellar multiplicity must be taken into account in our models, no matter what you're doing. And this is something that was already formulated in the 70s, that all stars are born as binaries of multiples. And if you think about there are two implications of this. The first is that most, if not all, single stars were once part of multiple stellar systems. So this is good to remember. And the second one is that ejection and stellar encounters are common in active star-forming regions. So what's a flyby? Let's define it first. So a flyby occurs whenever a star on a parabolic or hyperbolic orbit perturbs another star. So here, this one is in the reference frame, and this one is shooting and crossing the field. And there are basically two types of encounters. You could be either prograde or retrograde, but this depends on the sense of rotation of the disk you might have around one of the stars. So in this case, if this sense is the same as this one, we'll call this prograde. If it's the opposite, it's retrograde. And then you also have basically, so this is an example of a simulation we did a few years ago, where you see that there is an encounter. I will show you the movie in a bit, but you see that one of the stars steals some material. But you also have three categories based on how close you get to the other star. So this is a non-penetrating encounter, a grazing encounter, and a penetrating encounter. I'm going to discuss some of these that were done by Elie Borchert a bit later. Another cool effect for Jan. And so this is spiral formation. So this is kind of things that can happen. You can have spiral formation. You can truncate the disk. You can misalign the disk. You can create dust traps in the disk as well. But I'm going to focus today on accretion events. And the typical sizes are basically 100 AU here in size. So the criterion we tend to use is if anything gets closer than 1000 AU, we call that a flyby. So let's move on. So this is an example. I'm going to go quick on this. You see the little star coming here. It perturbs the disk, creates spirals. All the things that I've been saying are illustrated here. And you see that the star that initially did not have a disk lives forever with a disk around it. So this is what we call a circumsecondary disk that was formed during the encounter. And you can also see this from the side, because actually this thing did not happen in the plane. It was 3D. So you see that you generate this kind of spirals or bridge between the two stars. You have some spirals here. You send out some material. And actually, we did an extensive work with many of the collaborators here in the room, trying to establish basically which were these kind of morphologies and which were the fingerprints in terms of observational diagnostics. So now let's focus on the main topic of today, the powerful link between accretion and stellar flyby. So these are old results we got more than 6 years ago. We were basically plotting here the logarithm of the mass accretion and as a function of time in linear scale. So here you have in different colors, different orientations. So red is basically prograde and blue is retrograde, as I was telling before. And you see that for red orbits, so prograde orbits, you have this kind of huge peak shortly after the passage at pericenter. You see that you can increase by a factor of almost 100 the accretion rate of the central star that's being perturbed. So this is something cool because we know that some stars do these kind of things. But there was a main problem here, and it's that basically between the passage at pericenter and the peak of accretion, you have basically 100 years. And this is a bit too long. We want something to occur faster than this. This is basically the recipe we were using to estimate this. Basically, you can convert the accretion rate into luminosity and then see how much you should increase the temperature as well. But these ones were problematic. So the conclusion of this is that distant flyby triggered outbursts are in tension with the Epi-Orionis outbursts that I'm about to show. And this happens no matter what you do in terms of mass ratio. You can take the best case we had before, so the one inclined prograde, and you increase the mass of the perturber. You see that you can make happen. This thing happens faster, but still it's a bit unrealistic because you need really a massive star to go very close to the disk, and this is statistically unlikely. So this is what actually was observed in almost a century ago. In 1937, they were monitoring the blue magnitude of this star, Epi-Orionis, and all of a sudden, basically in 1 year, we went from there to there. So you have increase of magnitude 6, and so this basically translates into an accretion factor of 100. So this is super spectacular. So it means that all of a sudden the star is 100 times brighter. And you see that since then it's been going a little bit down, but it basically remained at this high accretion state. And you also have some level of variability on a shorter time scales. So these are months. Well, so this is the scenario we want to reproduce. And one thing to emphasize, as Daniel mentioned before, is that in Epi-Orionis, the less massive star, the one located to the north currently, is the strong accretor at the moment. And this was a bit puzzling because in the previous scenario, it was the more massive star, the one accreting more mass. So this is something to be remembered. And the separation between the two disks, when we have a lot of things we can infer from observations. So these are the observations we have at the moment. This is a sphere observation where you see we have the two stars here. There is a bright spiral arm here. And this guy here is the strong accretor, if I'm not mistaken. And it's the less massive one. And you also have some ALMA observations of this. So this is not the same scale. We change the scale, but we basically see that the two disks have compact dust thermal emission. So we need a model that could explain everything. And that was basically Elizabeth Borchert PhD work together with Daniel. So this is one of her simulations where she, for the first time, she coupled Phantom and MC-FOST. So this was super cool because it was the first time, one of the first times, because there are other works in parallel to this one, that we could actually monitor the changes in temperature in this perturbed system. So as you see, Elizabeth was working with penetrating flybys. So in this case, the star would penetrate the disk. So you go through the disk, and this is what happens in terms of density. And here she's showing basically the accretion onto the primary and onto the secondary. But we can also do this in terms of temperature, because you expect such a violent phenomenon to translate into a huge increase in temperature. So again, you have the perturber crossing the disk. There it goes through the disk midplane. That's why you have a boom all of a sudden, because you're getting from below and then crossing the disk at some point. You see that you steal some material and you live forever, but you had a fantastic and dramatic increase in temperature. So this is what you actually measured. So now you see that we have basically the same plot: accretion rate, temperature, time, passage at pericenter. But now you see that we flip the roles. So before we did not have basically any or significant accretion around the secondary, was mainly the primary. And here it's the other way around, is the secondary. So the perturber, which is accreting more material and having this kind of flash. And you see that in terms of accretion rate, we have, this has been fine-tuned, of course, but we have a factor of 100 in between here and here. And again, this is the recipe we use to compute the fast, how long it takes basically to have this rise time scale. So of course, it depends on the distance of minimum approach, the mass involved, and the luminosity you want to trigger using the formula that was in the previous slide. And Ellie did a very good work in basically recovering the theoretical expectation. So this is what we expect to happen, and then this is what she measured for the time rise in her simulations. So we were very happy with this, because we were basically proving that a disk penetrating flyby could, in principle, generate this accretion outburst. But the story does not end there. We kept working on flybys, and then we can now ask ourselves, what if both stars have disks? So the first one is that, as you notice, in Orionis, both disks have, stars have disks, as I showed in the observations. And for a given star, it's more likely to encounter a star of about the same age. So if one has a disk, the most likely thing is that the other one also has a disk. So I'm going to go a bit fast on this, but Ellie did a second work where she was basically playing with all the possible orientations. So here you have prograde and no disk around the perturber. Here you have prograde and same rotation between the perturber and the main star. Here you do a prograde encounter, but you flip one of the rotation sides of the stars, of the disk around one of the stars, retrograde opposite and retrograde same. I think you got basically what we're doing here. We're playing with the relative orientations. Here you see the face-on view, and here you see that you increase the time as you go down, and here you have different cases. So you see at the same time, for instance, if I zoom in, this is basically, so you can do this edge on, face on or edge on. And if we zoom, this is basically what you see. You see that retrograde are different from prograde, but also that the rotation of the disk itself around the secondary also matters. This is even more spectacular if you look at the kinematics, because when you look at kinematics, basically ALMA channel maps, you will see very big difference between here and here. So you can basically use this to reconstruct this crime scene, basically using scatter light and ALMA observations. But again, she was very interested in accretion. So she did that job and she looked at which was the best case for which you could have the best accretion flash around around the secondary star, basically. And that's the main takeaway, that having a disk prior to the encounter will change the accretion trend you should expect to the encounter. So if you're interested, you should go and check her work. So here you have the accretion to the primary, accretion to the secondary, and the total luminosity, as in, for instance, a simulation, an observation where you're not resolving both sources. You might see weird stuff going on, which is actually what happened for Orionis. People did not realize back then that that was a binary. It only came around the years 2000, I think, as a binary. But that's what people were looking at. So my point here is that stellar multiplicity might play an important role in this kind of weird outburst scenarios. And one of the points I would like also to emphasize is that flybys move the ice lines quite significantly within the disk. So again, this is Ellie's work. She's now plotting the water ice line, I think, or the CO. I don't remember exactly which one it was. But the point is that basically, depending on how you have these kind of orientations and how you exchange energy between the two disks, you might have different ice lines, and you see that the ice lines are far from being axisymmetric, sorry. So you see asymmetrical patterns, and you have that some scenarios are cooler than others. So retrograde opposite is the hotter scenario in the sense that you move the ice line very far away in the disk. And this should have an impact on what happens subsequently in this disk and how you will form the first planetesimals. And you're basically reprocessing the dust, and that should be taken into account. And I think Pedro later this week is going to talk about what we're doing in the context of binaries with a bit this in mind. Another cool effect. So now let's go to the implications of the last point here. So are stellar flybys really a nightmare or a dream for planet formation? Okay, I'm going to go quick. So we did basically a gallery of monstrosities with Daniel and Francois. So these are our systems where we think things are being perturbed by flybys. You can also look at what happens in dust continuum. I'm not going to go into detail. I'm running out of time. I'm just going to show you some systems that we think are interesting. So this is the list we did. And we basically, most of our suspects have pericenter distance and the disk size, which is about 1. So they're grazing encounters. And the only one which is penetrating, we think it's a Furionis. If it's a flyby or not, that's to be established. And I'm going to go through very quickly 2 works we did with Jeremy Smallwood and also Ellie. Here, the question is, what happens if you already have a disk beforehand or if you do not have a disk? So if you don't have a disk, you gather some material, that's fine. You have a new disk, everything's coplanar here. But if you now incline the orbit of your flyby here, you're basically having an inclined flyby at 45 degrees. The angle at which you capture material is twice that angle. So if you're interested, go and check Jeremy's work. We also did this with an existing disk beforehand. So in this case, you force the material basically to be accreted onto that preferential plane. And Jeremy also looked at the spirals you trigger and how long they stay in the disk, and if this has implications for planet formation or not. And you see that you can trigger eccentricity, you can do disk truncation, and so on. Go and check his work, please. And to conclude, this, I think, is my point, that planet formation is aided by flybys. There are a few things we can discuss and do over the week, mainly how you can concentrate dust. So this is dust as a function of radius. And after the flyby, you see that this is the unperturbed case. You send a lot of dust to the inner regions of the disk. This, I think, is significant. And also, Daniel has been working on how you might be able to form CAIs during these encounters. And more recently, I've been studying resonance chains that are perturbed by flybys. Please check the work by Carolina Charlambaus if you're interested. And as a conclusion, I think that flybys are sometimes gravitational vandals in the sense that they trigger outbursts and substructure around young stars, but they can also help to deliver planetesimals by triggering gravitational instabilities, concentrating dust, and accelerating planet formation. And it's important to consider both disks, as I showed before, and because one needs to take into account radiative effects, chemistry, and many, many effects. And the last point is that I think we need to focus on a search for a more systematic link between flyby candidates and recent or ongoing flybys. And we can also discuss if are outbursting stars the norm rather than the exception. That's a good point to think about it. And perhaps our own sun was an outbursting star. And with this, I conclude. And thank you very much for your attention.
Time for 1 or 2 questions.
Initially, you showed for the accretion rate that was gradually increasing, but then in the second part of the talk, you matched this sudden increase in accretion. What was the difference? Was it like the penetration?
Yes. So basically, we go from I would say 2D accretion. You would accrete that in a 2D fashion versus a 3D fashion. So what we typically did before is you perturb the disk and you expect that wave that you create in the disk to be transported and perturbed and eventually lead to accretion onto the star through the disk. The difference here is that you have a disk which is living here peacefully, and then you throw a star at it, and then as the star crosses the disk, you accrete material more in a 3D fashion. So you have material which is basically landing directly onto the star, and this is what triggers the immediate flash, basically. There are also some people working, Edward Vorobyov, for instance, perturbing the disk very far away that compression wave doing thermal instability and other mechanisms that we're not considering here. You can have also a delayed delivery of material onto the star due to a distant flyby. But in the case of Orionis, our idea here with Eli was really to go through the disk to make this as soon as possible and as wild as possible as well.
I have a question related to the radiative transfer part. You showed the animation of the star passing through the disk and temperature boom, right?
Yeah. So I think it's the second one. This is the temperature.
Does the simulation consider the finite speed of light? In this case?
The finite speed.
And if so, would it change the shape of the?
So I know there are some people working on shadows that might cast delayed effects onto the disk. You might have spirals, which are basically a combination of this finite speed of light and differential rotation. In this case, I think, correct me if I'm saying something stupid, but I think we stop the simulation at a given snapshot, then we compute the temperature with MCFOST. So we treat the disk as a whole, and we don't have photons propagating first to another place and then to another. We wait till we reach the equilibrium, and then we keep running the simulation as a hydro. So in the loop, we do not include such details. But it could be something to be considered, perhaps. I don't know how exactly, but yeah, there are some effects like this one should be careful